Thank you for inviting me to give this lecture. I mean, it's so this is not something that is related to QMC pack. This method is not in the code. It will have probably, I don't know, maybe eventually. We discussed yesterday whether this is something that we are going to try to put in the code. But at the moment, this is really a research subject. It's something that we have done in collaboration. I mean, these are the collaborator people that are actually contributing at this method. We collaborated with Norm, which is here also, other people, and there was some more people that I didn't put, I forgot. So, and this is a long-term collaboration, I would say. I started this with David like 15 years ago, maybe, or a bit less. But the real difference today is that the computers are changed a lot. So now we can really do something that we couldn't do 10 years ago. So I think this is now the real moment in which this method can give some interesting results. So I'm not going to describe the results. I had a poster until yesterday which was hanging outside. I don't know if you have seen this. So I'm not, I mean, Paul asked me to present the method, not the results. So I'm going to discuss what are the elements that are unique to this method and are different from what you have heard so far. Okay, so this is my outline. So in any event, I want to give you some motivation why we had taken this, developed this method. So the motivation is to study hydrogen. And in fact, so far, this method has been applied only to hydrogen. And this is one of the reasons why we need some method development, some code development. And so there will be an introduction. Then I would like to emphasize that we can do non-Born-Oppenheimer methods like restricted path integral or diffusion quantum Monte Carlo in the case of hydrogen. And we can also do Born-Oppenheimer method, and this is what is the couple Electron-Ion Monte Carlo. And here are the elements of the couple Electron-Ion Monte Carlo. So we have worked quite a bit in developing a good wave function. Then we, of course, do an electronic calculation. But you understand, Born-Oppenheimer means that you have this separation of time scale, as Miguel was explaining yesterday. So this method is actually doing a quantum Monte Carlo for the electronics part of the calculation, and then the energy that you get from this method you use to sample the thermal distribution of the nuclei, either classical or quantum. And so it's a kind of, that's why it's called coupled Electron-Ion Monte Carlo. So you have to do QMC either at the variational level or what we implemented in reputation. And we had to also to develop some special algorithm for do the reputation. I think nobody talked about reputation. David, did you talk about reputation? No. Okay. So maybe I can give you some hint of what is reputation. Then we had to do something special for sampling the nuclei, and this is because you have noise in the energy. And then we had to do some development, how to introduce nuclear quantum effect in the method. This is basically what I would like to talk today. So first of all, why we want to study hydrogen? Well, hydrogen is a quite important element, I would say. But first of all, it's the simplest element. So you will like really to be able, I mean, as a computational physics, you want to have a method which is able to predict things. So to solve at least the simplest element, this is something that would be nice, right? It's very important because it's very abundant in the universe. So in the giant gas planet, a lot is hydrogen. And if you want to do a very good job in having models for predicting the behavior of these planets, how they form, how they develop, you need very accurate equation of states. Of course, hydrogen is also relevant for other applications like energy, nuclear fusion. And as I said, is the prototype of quantum theory. So people have started doing the hydrogen atom and then the hydrogen molecule. So we would like to do something better. We would like to do the condensed phase in a predictive way. And in fact, it has been found that hydrogen under pressure has a very difficult, or maybe not that difficult, but people were not expecting that the phase diagram is so rich. In fact, it's like many other first row elements, that they have all these crystalline phases, and then people are finding this now, and in the years have found this. So there is a rich physics anyway. So this is a kind of sketch of the phase diagram of hydrogen, and here you have the normal three-phase of the molecular insulating element, and then when you increase the pressure, this is the solid, as a rotationally invariant solid, so the molecules are freely rotators, and then you have a bunch of phases here which are not yet completely understood. When you increase the temperature, you ionize the molecule, you break the molecules, then you adionize, you go to a plasma phase. This is kind of, the Fermi temperature is here for the electrons. Then if you increase the pressure, you go to in a degenerate two-component plasma. So there is a lot of physics. And here there is this line which is what is called a first-order phase transition line between two fluids. The H2 fluids insulating, and here it's a kind, should be a metallic phase, monotonic. So you have a metal insulator transition, dissociation transition, various crystalline phase, so all this transformation of crystalline phases, everything. So it's really a lab. You can do whatever you want. I mean, there are a lot of physics, and there is superconductivity also, of course. People have found that if you compute the coupling, electrophonon coupling, that's very large, because the phonons, I mean, the nuclei, the protons are very light, very anharmonic. There is a lot. So the critical temperature for superconductivity is very high. So probably a large part of these low temperature phases are all superconducting phases, even the liquid phase. So no one really knows, because in fact, these are the kind of limitation that are, well, with the experiment that we are having. Here is a low temperature, they do diamond anvil cell experiment like Luke was showing with the xenon, but they cannot really go much beyond this vertical line here. And then the dynamical experiment, they basically follow the Hugoniot line here. This is a Hugoniot is when you have a sample and you send a shock wave, and then the shock wave goes through the sample, and the sample after the front of the shock is under a very strong compression, and the temperature increase. So it's a control line, but it goes like along one line. So you have information along this line. And then people that do these experiments, which are quite complicated, they have invented different way of sending this shock. And so now they can also explore large part of this area here. And so, in fact, last year there were several papers talking about the liquid-liquid phase transition in hydrogen. We started talking about this phase transition like 10 years ago, but of course we have done a lot of work on this. So, as I said, I would like to sketch, before going to coupled electron-ion, two different methods that can be used to study hydrogen or other elements without applying the Born-Oppenheimer approximation. One first method is the imaginary time path integrals method that you have already heard a little bit. For fermions would be restricted, so a kind of fixed node approximation. In this method, you start, so it's the Feynman path integral, so you start at high temperature and then you develop your imaginary time path to decrease the temperature of your system. But then you have to start, if you have, now here you have protons and electrons. So you should start almost in the classical limit of the electronic part, because the protons, well, can be quite classical at high temperature. But the electrons, you have seen the Fermi temperature is up above. So you have to start up there and then develop this imaginary time path. And then if you want to compute properties of your system, then you have to do this integral. And this is the thermal density matrix. And then you can write the action. So this is in terms of some action in this way. And you have to do this kind of imaginary path. And then you sample this imaginary path, all this integral that appears in this form here. You have to break this imaginary time action in many little pieces, many steps, and then you have to sample. This is the sketch. You have all. This is the imaginary time axis. This is the coordinate, the many-body coordinate axis, and then you have to sample all this intermediate time, and then do this integral and compute the properties. Then you have to do the fermion fixed node approximation, and actually David developed this method long ago. That's why I put these two papers, which are where you can find the detail of this methodology. We applied long time ago this to hydrogen, but then you realize very soon that the fact that you have to start in almost classical electron and then go down in temperature, taking longer and longer path, well, you hit a limit, a practical limit. So these calculations can be done, are accurate, and people are doing this, are still doing this, but you cannot go much lower than, I put 20,000 or maybe 10,000 Kelvin, which is, on our phase diagram, is pretty high in temperature. So you can do a large part of the phase diagram, but high temperature. The other method is, well, you will learn about diffusion Monte Carlo. So now you can do diffusion Monte Carlo for protons and electrons simultaneously. You have to have a wave function, a tri-wave function for the electrons, a tri-wave function for protons, and then you run your DMC. But again, there is a separation. Well, the temperature effect is absent. Both components are in the ground state, but then you have a time scale separation because your imaginary time dynamics. You have to take a time step which is suitable for the electrons, and the protons don't move too much. I mean, this is, again, I didn't put the reference, something that, no, he's here, something that David pioneered in 1987, and I don't think anybody has repeated this. So this is something that now it should be very feasible and interesting. But again, you don't have the temperature effect. So you do the ground state, or you do the 10,000 Kelvin. So now the idea is, well, much of the interesting physics is happening around here, right? Where you want to see all this phase transformation. So you would like to have the temperature for the nuclei, but not 10,000 Kelvin, because otherwise you lose most of the condensed phases. And so why don't we use the Born-Oppenheimer approximation, as everybody does, and as Miguel was showing yesterday? Of course, you can do molecular dynamics, we heard about, or we develop this coupled electron-ion method. Now there is a competitor method which has been developed by Sorella more recently, which uses forces. That's something that Miguel mentioned yesterday also. I mean, the two are on the market. And with coupled electron-ion, we can fill this gap that otherwise are left by path integral and DMC in the ground states. So that's why we have done all this work in these years. Okay, this is what is coupled electron-ion. So as I said, we do a metropolis Monte Carlo for finite temperature ions, and the Born-Oppenheimer energy in this metropolis Monte Carlo is obtained by ground state QMC for the electrons. Now, variational reputation, as you have learned in these days. Of course, here there is one peculiarity of our method is that, well, you have seen already that you should, well, we don't have pseudopotentials here. Hydrogen is simple. We have 1/r interaction. So this is one simplification with respect to the difficulty of QMC. But we have to do 1,000 or 10,000. I mean, in order to compute the averages property, the thermodynamic properties of the system, we have to generate 1,000 of nuclear configuration, which are roughly statistically independent. So you have to repeat the quantum Monte Carlo calculation millions of times. Okay? So how many steps, how many electronic steps you do for one nuclear step? A lot. And then how many nuclear steps you want to do? A lot. So it's a lot to the square here. We have to do a lot to the square. So it's a challenge, right, for computers. So if we have to do through optimization of the wave function, then we have to do projection, That's a lot. That's really a lot. So we have worked a long time on developing very good wave function for hydrogen, which is simple. And so we have reduced very much the cost of variational Monte Carlo, of optimizing the wave function. Also, we have found some strategy that in hydrogen is very good. And at the end, we don't optimize at all during the calculation, on the fly. This is different from what Sorella does. Sorella does optimization, heavily optimization at every step. Also, I would say, in our latest work, we don't do projection on the fly. We do projection later. So we correct for projection energy. Okay. This is in order to get useful results. No, these are the element of the method. So we do variational Monte Carlo, reputation, then we have invented an algorithm to do reputation, although now we don't use it much. Another key important property or trick of the method is that we need to compute energy difference in a very, well, the most accurate method and robust. The other thing is that every little piece must be very robust because you want to repeat this procedure many, many times without the human intervention. You cannot stop your calculation every nuclear steps. It must be automatic. So it must be a very robust method to compute energy difference unbiased, otherwise your sampling is biased. And this I will mention very briefly. Then, okay, we do twist averaging because we want to reduce the size effect. We don't have the two-body size effect built in. It could be done. We haven't done so far. We put the two-body, the two electrons, as Luke explained this morning. We correct the thermodynamic result after by this little shift. But it's a little shift, as I said. So once you have done your electronic calculation, then you have to move the nuclei. And here there is some method that you have to use because now you have suppose that you have one protonic configuration. You propose a new protonic configuration, which is done with some reason. Then you have to do a metropolis test. You have to accept or reject this move. Now, the energy difference that you compute here is affected by noise. And this noise, if you disregard this noise, is going to give you a bias in the sampling. So you have to take into account the noise, and you have to modify the metropolis rule in order to accept the move or reject and take into account the noise. And this is called the penalty method, which has been developed by Dave and Mark a long time ago. The other elements of the method is that hydrogen is a light element, so quantum effect on the nuclei are quite important at that pressures. So we are talking of 100 gigapascal or more, 1 or 2 megabars. So these protons effects are important and need to be taken into account. And so we have developed a strategy to use imaginary time path integral at finite temperature for the nuclei within this method. So not only can be point particle classical, but they can be little ring polymers that has to move in this sea of electrons. Okay? So I don't know. Variational Monte Carlo, I wouldn't say nothing. Now, what is reputation? Well, reputation is very similar to diffusion. In theory, all these formulas you have already seen. Simply, you need to compute the ground state energy, so you want to take your tri-wave function, project with this operator a little bit in time, and then compute this average here in this way. So now, if you project half of the time left and half of the time right, then you see that you basically need to compute, let's say that you need to compute this function, and then its derivative with time. The first derivative, the derivative of this function, the log of this function is the average energy, which will be the average of the local energy, and the second derivative is the variance. And then from here you can see that this E of t converges from above always. So what we do for computing this integral here Well, you can work in coordinate representation. So now these are the 3n coordinates of the electrons for given nuclear position. So here you have a nuclei are fixed at external fields, and you want to compute this integral for each realization of the external field. So you write this, and this is nothing but the thermal density matrix, where T now is the imaginary time of the electronic part. Then you do factorization, so you rewrite this in terms of path integral, you do the throttle breakup, and then you end up with a kinetic propagator, which is a Gaussian, and then you have this weight for each little step, which is tau. Now you have to repeat this tau m times, and then you get your imaginary projection time in this form. So you have to do all these integrals by Monte Carlo. So you have an open path in imaginary time, which represents the electronic configuration for given nuclear state. Okay, you can do important sampling. Again, if you do important sampling, you rewrite your Hamiltonian in a slightly different way, and then you get your local energy in the exponential, like in the diffusion Monte Carlo. But here we don't use this part to replicate your workers. We don't have workers. We have one representation of the electronic path, and we have to move this representation. So we don't do a dynamics in imaginary time. The dynamics is explicit. You say, I have T. T is fixed. I generate a path integral, and then I find algorithm to move this path in the configurational space. This is the difference, the practical difference with DMC. Otherwise, it's the same theory. And okay, so you keep this weight in your action, and you move your path. What is here? Here I can skip. So at the end of the day, your reputation Monte Carlo is simply, as I said, you build a path in the for the electrons at given S nuclear configuration. You sample with some distribution, which is what? Is the exponential of the tri-wave function left and right, the two ends of the path, and then you have this action, which is given by the action along the path, each linked. And then you have to compute properties. Now, if you compute properties in the middle of the path, like I wrote here, these are unbiased estimator. Of course, you have to do quite long PAMI. You have to increase your projection time. You have to repeat your calculation with different projection time in order to converge to the ground state. But these are unbiased estimator. Okay? Then if you have fermions, you have to add one more step, because when you move your path, you don't want that your intermediate points cross the nodes. You have to be sure that you don't cross the nodes, otherwise you have a sign problem coming in. But it's precisely the same algorithm. Now, you have to find a good algorithm to move this reptile. It's a reptile, it's a long snake, right? And these are, well, there are several techniques to do this, but what we have done is we have developed in this paper an algorithm which is called bounce algorithm. I mean, what was done before is that well, first of all, this method called reputation has been developed by Moroni and Baroni in Trieste, and they were inspired by Monte Carlo methods for polymers, and that's why they call reputation, because this is a kind of movement that long polymers do. And what they do, they were doing, you have your path, you say, I want to go left. I want to move to add a piece on the left and remove a piece on the right. This is a legal move, because if I do this satisfying the Dale balance, I can do. And then the next time I decide which way I want to go. Every time I have to move my path, I have to decide which way I have to move, I have to go, and then do the move. This is actually not the best way of doing, as we have found, at least for electrons. In the case of polymer, it's different, but at least for electrons. And what we have found is that you can develop a different strategy. You can, instead of choosing the direction at every step, you can go always in one direction until you reject the move. Then when you reject a move, you go backward. This algorithm does not satisfy the Dale balance, but is still you can prove, and this is the proof in this paper, you can prove that it still give you as the same long time distribution, equilibrium distribution. So as the same eigenvector. So is a question of which eigenvector of the transition probability in your Markov chain you are sampling. And so you can show that you are sampling the same long time distribution. Okay, this is just a nice piece of work that we have done. So you see here, we are talking 2005. We were already doing couple electron-ion at that time. Okay, now the energy difference. So this is the way we sample. Either we do variational Monte Carlo or we do this bounce algorithm for the electrons. Now, the energy difference method, well, here, as I said, we have, the problem here is that we have to compute the energy difference between two nearby protonic configurations, which I call S and S prime. They can be the same configuration, just moving one proton, or they can be nearby configuration moving all protons. This is something that you have to choose. And it depends very much on your wave function, I would say, because now, in any event, the energy, if you move, if the two configurations are too different, the energy difference will be very large, and you have a high probability of rejection, as in all Monte Carlo tests, Monte Carlo methods, right? So usually you work in the case in which the difference of the energy is much less than the energy itself. You move a little bit, your protons. And then if you want to compute this energy difference, which is with a small small variance, doing two separate calculations, electronic calculation, this is really time consuming. So it's much better if you decide that instead of sampling your electrons from the external field of the first configuration and the external field of the second configuration, you combine the two wave functions or the two weights in a unique distribution. So we have one electronic path which knows both nuclear configuration. You can show that this form of the probability distribution for the electrons is the optimal, the one that minimizes the variance of the energy difference. But this is a kind of difficult to use because here you should compute, you should know the average value of the energy before sampling the electrons. This is kind of, you can implement in a self-consistent way, but we found that if we use just, you remember this pi is, in my notation, is this pi here. Is the probability distribution for your electronic path that you have to sample, okay? Now, when we do energy difference, we sample the sum of the two pi's for the two different nuclear configurations. And this actually is nice because, first of all, your energy difference is always bounded, and the electrons knows the relevant space for the two nuclear configuration. So you are sure that you are visiting all the important parts that are relevant for computing the energy. And then you get, from this sampling, you get directly the energy difference. Of course, then you want to compute also thermodynamic properties, so you want to know, like, the internal energy, how much is the internal energy, and then you can compute the properties for the system S, for instance, or S prime, as you want, by doing reweighting. And this is why we decided to use reputation quantum Monte Carlo rather than diffusion Monte Carlo. Because when you do diffusion Monte Carlo, you generate this trajectory, but you don't keep memory of the past. Now, suppose that you want to reweight your sampling. You cannot do this. I mean, you can do, but it's much more difficult. Instead, in reputation, your explicit electronic path is, your electronic path is explicit. You keep everything in memory, so you can do reweighting quite easily. It's very easy to do. Now, whether it's efficient or not, this is a different story. But coding is much easier, okay? So that's the only reason why we decided to use reputation rather than diffusion. Okay, final size effect, I don't have to say much because we use twist averaging. There is no extra cost for twist averaging couple electron-ion. Why there is no extra cost? Well, you have to compute the energy difference, and you have to, I will tell you in a minute why, but the reason is that the energy difference, you have to compute the energy difference, the noise over the energy difference. Not only the variance. You want the noise to be not too large, for reason that we will see in a minute. So you have to repeat your electronic calculation many times anyway, because you have to decrease your noise. So why not doing 100 twists, different twists, and then accumulating the energy difference? And then this is automatically reduce the noise and you reduce the size effect. So that's why there is no extra cost. Because in any event, you have to do all this job. So better to change the twist. Okay, now moving the ions. Now, as I say, this is Boltzmann distribution. Suppose now the ions are classical, okay? How much time do I have? 15 minutes? Okay. So suppose that the ions are classical. So that's the Boltzmann distribution for these classical ions. Normally, what you should do in Monte Carlo, Metropolis Monte Carlo, you propose a new configuration with some transition matrix, and in the simplest form, this transition matrix is a symmetric matrix, and then you accept or reject with this rule. So you take, if you go downhill, you accept always. If you go uphill, you have to accept with this probability where the difference between the two Born-Oppenheimer energies appears. That's why we need to compute the energy difference. Now, you can prove that if as David explained the first day, if your transition rule is ergodic, after a finite number of Markov of steps, your chain is sampling this distribution. This is the limiting distribution, which will correspond to the eigenvalue equal 1 of the transition probability. Now, if you have, in the penalty method, the Born-Oppenheimer energy comes from a quantum Monte Carlo calculation. And you have noise, because it's a statistical calculation. It's not like, if you do this with DFT, you have the energy. There is no error. There is no noise on the energy with DFT, right? Because you compute it. Of course, there are some systematic bias. You have a cutoff, the energy cutoff, you have some other bias, but there is no noise. Here, the bias might be smaller, but the noise is present. So you have to take into account this noise. So you have to use what is called penalty method. There are also other methods, but this is what we use. And this is explained in this paper by David and Mark in '99. What is, very short, what is the penalty method? Well, first of all, you have to assume that for each pair of configuration, the average of this difference exists, and we call capital delta, and the variance also exists. So the noise, the distribution of the noise, the distribution of this delta for this pair of configuration give you finite numbers for these two averages. Now, what you want in the standard metropolis, you want that the acceptance probability satisfy this, which is called detailed balance. In fact, you can write this in a different form, but basically is the form which I wrote here without the average. But now, we don't want to satisfy detailed balance for every single realization of the energy difference. We want that this to be satisfied on average over the probability distribution. And this is what I wrote here. So you have this acceptance on average. And the acceptance on average is nothing but the acceptance for a single delta realization averaged over the distribution. You can prove, and the proof is in the paper, that the only difference in your code must be that you have to add this extra penalty in the metropolis rule, and this sigma square is nothing but the variance of the energy difference over the noise distribution. So suppose that you have these two fixed nuclear configuration, you do one electronic energy, one calculation for the difference. You repeat this calculation 1,000 times. This is 1,000 different realizations of this calculation. You compute the average, you compute the noise, and then you accept or reject with this rule. This is the penalty method in short, let's say. And this, you are guaranteed that you have unbiased sampling of your Boltzmann distribution with the Born-Oppenheimer energy. Now, you see that there is always an extra rejection. So the noise causes extra rejection. So if the noise is very large, so if you do a very short QMC calculation, then you always reject because of the noise. If you want to reduce the noise too much, you have to do a huge, humongous QMC calculation, because we have heard that the noise is going like square root of the number of samples. So it's hard to kill the noise. But you can do this, but then you will spend all your time doing QMC calculation, no sampling of the nuclei for one pair or maybe 10 pairs. You want to do something in between. So you want to have a level of noise which is not too small, because otherwise you spend all your time in sampling the electrons and no nuclei, and which is not too large, otherwise you always reject. And be careful, because here there is a 1 over kT in front of the energy difference. So here there is 1 over kT squared, the inverse temperature to the square. So if you go down in temperature, this term increases. Okay. That's what I wrote here. So there might be a problem if you want to go too low in temperature with this method, because you have to run longer electronic calculation. Now, in practice, we have implemented another trick, is that we use two-level sampling, two-level metropolis sampling in our calculation. We split this distribution in this way. So we introduce a sort of effective potential, which I call classical, but can be everything, which is much faster to compute than the Born-Oppenheimer energy. And we do a pre-acceptance test. So we propose a move with some rule, and then we pre-accept the move with this distribution. And then only if this acceptance is passed, then you go to the second level. This speeds up the calculation a bit. And this is the penalty method on the acceptance. Okay, here for the two-level sampling, in the actual calculation that we are performing right now, what we do is we use this transition probability, which is, you might recognize this as the DMC propagator. But here we use the force from DFT, because in our wave function, we have the orbitals from DFT. So you get, simultaneously, you get the forces. We propose the move with the drifted Monte Carlo with the forces, and then we accept or reject. This would be the first level of acceptance, and then the energy difference between the quantum Monte Carlo and the DFT is used to finally accept the move. That's what we do at the moment. Okay? With this strategy, we can use system of 100 protons and get some reasonable and useful results, I guess. I don't know if you have seen the poster we have done. With this strategy, we have done calculation at high temperature, and then we have done calculation at lower temperature, like 200 Kelvin, which is pretty low, and for system of 96 protons. Okay, this is my last bit of complication. How do we treat quantum protons? As I said, we want to do path integral Monte Carlo. So now the protons are not anymore point particles. These are this kind of Feynman path. And each of these time slices has the electronic calculation, his own electronic calculation. So it's just replicated kind of like, I don't know, 10 or maybe 20 different replica of your system, and you have to do this electronic calculation for all of those replica. You understand why 10 years ago we couldn't do this calculation, because now we have machine of 1,000 cores, so you say, okay, I want to do 1,000 cores, I go. 10 years ago, we had 8 cores. We couldn't do much more. maybe 50 cores, I don't know. Okay. So here, what you have to sample in the nuclear path integral, you have this imaginary time temperature, thermal density matrix, the same formalism. And the thermal density matrix, you have the kinetic energy of the protons and the Born-Oppenheimer energy for the nuclei. And these are the two states. And here, this is the inverse physical temperature now. It's not the projection time for the diffusion Monte Carlo. This is the temperature, okay? So you are not free to take a longer path. You want to do 100 Kelvin. This is given by the physical temperature. To compute the average of diagonal operators, and this is what we compute for protons, we map quantum protons of a ring polymer. So this path integral will become, each particle will become a ring polymer, and then you have a lot of these ring polymers that you have to sample. Here I say we limit to distinguishable particle. Of course, if the protons are not really distinguishable particles, they are fermions, or if you have deuterons, they are bosons. But if the temperature is large enough, you can disregard the permutation in this space of particles. So for the moment, we have the diagonal term only. And that's why I say we have these little ring polymers. This is something that could be put in the method. We didn't do because we didn't think it was particularly relevant for what we wanted to do. But in the future, there is nothing that prevents. It would be a bit slower. That's the only problem. And then this thermal density matrix, you do the usual trick. So you break up in little steps. That's why I say I have these little rings. And then you want to compute the high temperature propagator for this process. And again, we introduce an effective potential, and we split the propagator. We split this Hamiltonian in this way, in such a way that we have the effective Hamiltonian plus the exponential of the difference in the two energies. Why we do this? Well, because the effective density matrix corresponding to this Hamiltonian, we know quite well how to model, and we can find good approximation with large time step. Okay, I don't want to go into the detail. That's what we use in effective pair density matrix. That something who is interested in this, we can talk later if you want. Okay, the remaining part we add at the level of the primitive approximation, and then with this strategy we can do, as I say, well, depends. The time step that really depends on density, but for the pressure range that we are interested, you can go to room temperature with 20 time slices, protonic slices now. This is a kind of test of convergence. You see, for doing 600 Kelvin, this is the liquid-liquid phase transition. You have the two branches. These are two liquids. One a low pressure. This is the volume per particle, basically. So here you have a low density liquid, which is molecular insulator. Here you have a high density liquid, which is monatomic and metal. But you see that here in this slide, I want to show that if you use 4 slices, the plateau here indicates the transition pressure. If you use 4 slices, this plateau is up here. Then if you use 8 slices, you go there, and then with 16, you stay there. So 8 is enough to go to 600 Kelvin. So if you want to go 300 Kelvin, you take 16, sorry. 16 slices is enough with this method. Okay, now, the last minute, I want to argue that quantum protons in coupled electron-ion are almost for free. Again, for the same reason why that the twist average is for free. Why? Because this is the noise level. Suppose that you want to run with this, which a fixed noise level for classical particle. Now you have p replicas. This is the number of imaginary time step. You have p replicas in imaginary time, and so your noise level becomes something like that. And now, if this is a fixed number, you see that the noise on each time slices that you can use is p times, I think here there is an error. Okay, so what I want to say is that the noise for each time slice could be p times larger than the noise, the equivalent noise for the classical particle. So you have to run p different electronic calculation, but for p times shorter. So at the end of the day, the number of electronic steps that you do is equivalent, except for the fact that you have to relax this path. So moving a path is more difficult than moving a point particle. But the number of electronic steps, in principle, is not increasing linearly with the number of time slices. And so in this sense, again, you gain in doing quantum protons, or you don't lose at least. Okay? I don't know. I think there is an error here, but anyway. So the last things, what do I have next? I have a summary, I think. Okay. No, I mean, if you look at the slides I put there, are much longer. I want to stop here because of course, I have only half an hour. So this is a kind of summary of what we do. What is coupled electron-ion? So you have an electronic path and electronic path and the protonic path. So in fact, you have for each proton, for each time slice, you have a different electronic path. You propose a trial protonic move P prime with a suitable transition probability, depending on the particular system. You run independent calculation for each P slices and for all twists. And so this is very ideal for massively parallel computers. Then you sample this electronic configuration with important sampling. You compute the energy difference, and then you accept or reject with the penalty method. Okay, so in practice, what we do is we have like 100 protons and 100 electrons. And as I said, I didn't talk at all about the wave function. We have a very accurate wave function. We don't do the optimization at each step. Our wave function has backflow built in, because backflow is giving you a lot of energy and reduces a lot the variance. Here, as you have seen, the noise on the energy difference is the key property. And the most accurate your wave function is, the smallest the variable, the smallest the noise. So you gain in working on the wave function. The best wave function will improve your method, improve your nuclear sampling. So you want to do this. So what we do at the moment, we move all protons simultaneously, all time slices simultaneously, all electrons simultaneously. So it is a global move of everything. Okay, I think I stop here because my time is over. And, well, I don't know. If you are interested, we can talk over lunch or tomorrow, anytime. Thank you for your attention. Any question? I think, okay, good.
How often do you have to regenerate the electronic configurations instead of just reweighting every time? Like,
never.
Never? Just
never.
You generate once at the beginning and then?
Yeah, I mean, you keep moving all the electrons with the nuclei. But because we use this combination with some of the two protonic configurations, the two electronic distribution with the two protons, your electrons are always fine. You always have the previous step. Mm-hmm. And you move according to some rule, and then you do the electronic calculation. So we never have to generate. That's why it's pretty robust. It's kind of automatic. I mean, it takes time, but you push a button and then it goes. You don't have to work. Okay, thank you.